camera is actually on.
Oh yeah, I'll turn it off.
2 seconds. Yeah. Hello. Good evening, all. Thanks for coming. This will be presentation will be of 2 parts. One for 699 and one for 759. 699 is literature review. I'll be discussing results about cubic graphs and consistency. And in the 759 part, we look at something called the lambda matchability. We will start with defining perfect matchings. Perfect matchings can be one letter spanning subclasses. We'll find this viewpoint beautiful and define what a class is. You first partition the vertex into 2 parts, x and x bar, and look at all the edges going from left to right. And the notation we use is partial of x, and we call x and x bar to be the shores of the partial x. And we say that partial x is trivial either of the shores is a singleton or a cube. Now, if you look at this cut, there are odd number of vertices on either side. And if you look at this perfect matching, the intersection of this cut is odd. 1, which is odd. And if you take another perfect matching, is 3, which is again odd. It is because of this particular lemma. This is just handshaking lemma, but you just make one extra assumption. You take a spanning subgraph where every vertex has odd taking. Then the number of edges of this cut that is part of the subgraph.
Why do you use the pointer?
Oh,
Yeah.
So, the number of edges of the subgraph that intersects with the cut, the parity is exactly equal to the parity of the shoe. And it is true for any, and we'll be using the forward direction a lot, quite a lot throughout the talk. So let's take a moment to appreciate it. We just take a spanning subgraph, which every vertex has odd degree, and we have a cut. The number of edges in this cut that belong to this spanning subgraph F has the same parity as one of its shores. Yeah. Peterson proved that every 2 connected cubic graph has a perfect matching. Do we need this assumption to connected? Well, yes, because this vertex, this graph does not have a perfect matching. When you delete this vertex, you get 3 triangles and can't match it. If you want a simple cubic graph, you have this graph. And Schönberger strengthened this theorem by proving that each edge belongs to some perfect matching in a 2 connected cubic graph. And in graphs in which each edge belongs to some perfect matching, we'll put some technical conditions and give it a name. We want at least one edge to be in the graph. That is one technical condition. And another technical condition is connected. So we call such graphs matching graphs. So these are graphs in which every edge belongs to a perfect matching. They are also connected and have at least one edge. And this is something we'll find useful later on. For cubic graphs, the vertex connectivity and edge connectivity are the same thing. So now we know that every edge belongs to some perfect matching. So we can define what are called perfect matching covers. These are just sets of perfect matchings such that each edge appears in at least one perfect matching. It's a collection of perfect matchings. And now you can ask the question, what is the minimum number so that this is possible? And for K4, you can cover it with 3 perfect matchings. In fact, it is much more general. If you look at all cubic graphs, you can apply the Mazzuoccolo theorem and they are either 3 edge colorable or not. If not, they are 4 edge colorable. So this we call it as class 1 and class 2 graphs. So you might know. And for class 1, class 1 is nothing but chi prime is equal to 3. Since it is a cubic graph, if it is 3 edge colorable, it is clear that each color class is a perfect matching. And that implies pi is equal to 3 and these two are equal. And the ones that are not 3 edge colorable, those are the strange ones, and they are called snaps in the literature. It comes from Lewis Carroll, the hunting of this. So coming back to perfect matching index, I'll just give you another example. Peterson graph, it is the smallest smart. And if you look at this cut, let's say M is a perfect matching. Can you tell me how many edges of this cut will M have? We should use the parity lemma. So one shore is the inside. No, I mean it could be any perfect match. So the inside there are 5 vertices which is odd, and outside there are 5. So it should be either 1, 3, or 5. And it is quite easy to verify that 3 is not perfect.
1 you can.
Yeah. And these are all the perfect matchings of Peterson. It has exactly 6 perfect matchings. And if you just drop one of them, let's drop M6, just consider M1 to M5. First thing we notice is every edge is covered. So it is the perfect matching index is at most 5. But you can, one can verify that if you pick only 4, you can't cover each edge.
Are these unique? Are these same and automorphisms?
Yes.
They're all the same.
They're all the same.
All of this. Yes.
You can draw this differently so that it looks like this.
This is a very strange situation.
Strange.
Too much symmetry.
Oh yeah, there's a lot of symmetry. Like vertex transitivity is where every edge is the same. So yeah, and the point is any perfect matching is the same, so I can without loss of generality consider M1 to M5.
I mean, it's perfect matching transition.
Yeah, that's right. So let's look at this edge. This edge, it is covered by M1 and M2, covered twice. And if you look at this bottom edge, it is covered only by M3. If I'm considering only M1 to M5. So, and if you look at all M1 to M6, each edge is covered exactly twice. We'll find that also useful later on. So, for Peterson, we saw it is at most 5, and Berge conjectured that it is at most 5 for every 2 connected cubic graph. So the name is pronounced Berge, and Peterson is also Peterson. I might say it wrong. But, so this is Berge's conjecture, and this conjecture, I'll call it the Fulkerson conjecture, but it was actually conjectured by both Berge and Fulkerson together. But I'll be talking about both of them so I'll just call one Fulkerson. So it states that every 2 connected cubic graph admits a collection of perfect matchings that cover every edge exactly twice. And by counting, you can show that collection has to be of size cardinality 6. I'll show you some examples. You are allowed to repeat perfect matchings. So I can, for K4, I'll put M1 equal to M2, M3 equal to M4, M5 equal to M6, and these are sets of these. This is a set of 6 perfect matchings in which every edge appears exactly twice. And in fact, there is nothing special about K4. It holds for all class 1 graphs. Just take 2 copies of each color class, and we are done. And as I showed you earlier, Peterson graph, if you take all 6 perfect matchings, you get exactly this property. And we'll call such a set collection of perfect matchings a Fulkerson 2 curve. 2 because each edge exactly appears exactly twice in Fulkerson. And does one imply the other? Can we see any pattern? So here is 6. Yeah. So you just throw away any one perfect matching here. Since each edge is covered exactly twice, if we throw away one, each edge is covered at least once. So this is clear. In fact, in literature, Fulkerson conjecture was always stated as a stronger version of the Berge conjecture. It turns out they're equal, and we'll see a proof. But first, we need to make some observations, especially about Peterson graphs. So recall it is equal to 5, the perfect matching index, and take any perfect matching cover of smallest size. Let's say M1 to M5 without loss of generality. Clearly, each edge is covered at most twice. We already discussed this, and we'll find this property very useful. So now let's look at any cubic graph, 2 connected cubic graphs, and let's say it has a set of 5 perfect matchings where that in which each edge appears, but it appears only at most twice. Of course, each edge is covered, so without loss of generality, I can make this assumption. I'm looking at a particular vertex. And now M4 has to go somewhere. I mean, it has to cover some edge. Let's say it is covering this edge. And M5 cannot cover this edge again. So it has to cover some other edge. Now, if you look at the set of edges that is covered exactly once, each vertex has degree 1 in that subset of edges. So it is a perfect match. Now I can throw in this F into this collection, and the scriptum extends into a full Fulkerson curve. We'll find this also very useful shortly. Now we'll look at edge cuts of size 2. We call them 2 cuts.
So that's a proof of the reverse
No. So
what is this showing this?
Yeah.
So Berge does not imply Fulkerson immediately. But if you have a Berge, let's say a set of perfect matching cover with this special property,
Then it implies.
yeah, then we have a Fulkerson.
So the birds thing go back again.
Yeah. Berge says it is at most. Yes.
So it says nothing about how many times the edge is covered.
Yeah.
It just says that.
So the bad case would be around around the vertex. This could be covered thrice. This could be covered once and once. If this happens, it doesn't work for us.
So this is an ingredient of the proof.
Yeah. If it is 2 to 1 everywhere, then it extends to a Fulkerson curve. Fulkerson 2 curve. And so we will use this property of the Fulkerson graph. We'll look at 2 cuts. First of all, by parity lemma, I'll apply to the entire graph. Now, cubic graph is 3 regular, 3 is odd. So these are 2 edges. So cardinality of x and x bar must be even. Now I can also remove these edges and add these edges to get smaller graphs, smaller cubic graphs in particular. And it's easy to prove they are also 2 connected if you start with the 2 connected cubic graph. So we'll call them marked C components, and we say that G is obtained by gluing G1 and G2. Yeah.
So you're thinking, assuming the graph has something,
Yes.
you can put some of the people.
Yes.
That's called C. Removing it, you see X.
Yes. And after I do that, I'm also saying you can also think of it as obtaining G from G1 and G2.
They take taking a two cut and then you're sort of
Yeah.
doing it. And
It doesn't have a mathematics, so that's why it looks.
Yes. Yeah, and you can also think of it as something reverse, going from G1 and G2 to G.
The perfect matches in G are in control corresponding.
Not exactly, not exactly, but there is some correspondence. There is a correspondence between the perfect matchings of G and certain pairs of perfect matchings of G1 and G2.
which have this C.
Yeah, I will look at it. Yeah. So these are just names, and by parity lemma, it is clear that either the intersection with this cut is either 0 or 2, which should be even. Right? So let us look at some perfect matching such that M intersection C is 0. So we have a bunch of edges maybe here. They exist here also. But these are matched this way. Now if you just take the restriction, it is a perfect matching in G1 and a perfect matching in G2. So I'll just define this. Mi is a perfect matching of Gi. Now let's take a perfect matching that contains both the edges of the cut. So in this case, I'll have these edges. But if I just consider the intersection, degree of every vertex here is 1, except these two. But I can add these edges back. Again, I have a perfect matching. This is exactly what I'll do. I'll take the intersection and then add the marker edges. We call these marker edges. So we have a perfect matching. So what we've done is we can start with the perfect matching of G, and we can map it to a pair of perfect matchings of G1 and G. And we'll abuse notation and call them restrictions of M to Gi. N is
Oh, N is the match.
Yeah.
So you're looking at matching either 0 or.
Yeah. And this is actually the word restriction goes for this, but not exactly for this, but we'll just call them restrictions. And now this is for a single perfect matching. Now if we have a set of perfect matchings of G that covers each edge, then can you say something about G1 and G2?
But they may not all be of this.
No, by parity lemma, this
So these
should
are the
go.
only case.
Yeah.
If you take the restrictions, then they will be perfect.
Yeah, they'll also be perfect matching covers. Moreover, there's one more thing that is true. It is okay. I did not mean to put Peterson graph this soon. Imagine it to be a box. Furthermore, we can say the number of perfect matchings that contain the cut C is equal to something in G1 and G2. No, so if it contains C, I'm throwing in E1 and E2. Right? So it is equal to the number of perfect matchings and the restrictions that contain E. So we have this. We'll find this also very useful. And now let's imagine Peterson came back. Like it was supposed to be one slide late, but okay. So Peterson graph has a perfect matching index of 5. So any perfect matching cover of G must have size at least 5. So we have this. And one more thing.
So you're counting all the perfect matchings in it that contains. And then you have this well-defined restriction.
Yes. And also not containing C.
That's okay, but there.
Oh, yeah. Yes. So if it contains C, what I'm doing is I'm removing C and adding E1 and E2. Therefore, it's exactly the same. I mean, I'm just looking at this particular collection. Okay. It's not all the perfect matchings in graph. It's for this particular collection. So,
No, I was thinking, is there a product formula here? From the another person?
oh yeah, that will happen. But here I'm looking at exactly one fixed collection. So yeah, so this is at least 5. And since M2 is a perfect matching cover of Peterson, recall that every edge is covered at most twice. Therefore, E2 is covered at most twice. By this, C is covered at most twice. I mean, C is contained in at most 2 perfect matchings in script M. And then that from there it translates to E1 also. So E1 is also contained in at most 2 perfect matchings of M1. Now we have made all the necessary observations and we are finally ready to prove.
Maybe wait a bit. Wait a bit.
Okay. Yeah. Yes. Oh yeah, I didn't emphasize that part. Okay, sorry about that. So if it is equal to 5 here, then script M2 also it is equal to 5. By the way we defined it. And Peterson has this property that if there is a perfect matching cover of cardinality 5, no edges, I mean each edge is covered at most twice.
In every perfect matching cover of the Peterson graph
Mm.
of cardinality 5, this is true.
Yes. So therefore E2 is covered at most twice, and that translates to C and that translates to E1. So we'll use both these facts in the next slide.
So this is called G by this procedure, this signal procedure with the Peterson.
Right.
Yes.
Yes.
Now for E1 we got what we wanted. Now you might guess what we are about to do. So the GB any two connected cubic graph. So I'll assume Berge's conjecture and Berge-Fulkerson conjecture. And for G is equal to K4, what I do is I take a Peterson graph and do this at every edge. And of course, I will call this G star. So pi of G star is at least 5. And assuming Berge's conjecture, it is at most 5. So it is equal to 5. Now I'll take a perfect matching cover of n star of G star of size exactly 5. Now what I do is I take the restrictions. Script M is a restriction to G. I mean, you can do it recursively for each edge. And script Mi, let's say these edges are labeled E1, E2, E3. So here this I'll call Peterson 1, Peterson 2, Peterson 3. So that I have here. Now I know script Mi is a perfect matching cover of the Peterson graph of size 5. So each edge is covered at most twice. Therefore, EI is also covered at most twice. And this is true for each EI. Now, from the earlier discussion, if we have this special property, then it extends to a Fulkerson over. When I first read it, I was like,
Proof by Peterson.
yeah, proof by Peterson.
But if you put instead of
By proof by
Peterson-
Mazzuoccolo.
But if you put instead of Peterson some other kind of thing, can you
Yeah.
make this technique?
Probably. I mean, so what we are using is across two pets we have this kind of behavior of perfect matchings. Plus, we are using the properties, particular properties of Peterson graph. Maybe if you want some other property, K33 might work or something.
You can take the numbers itself.
No, that just comes from the statement. Each perfect matching is of size n by 2. And the number of edges is 3n by 2. If each edge is covered exactly twice, it should be 6. So that 6 is kind of good thing.
Exactly. Here we don't have exactly.
Yes. Here we have at least once, but
At most times.
at most twice we kind of force by doing this thing with Peterson. So this is there, but there's a technicality here. So we did not assume Berge's conjecture for G. We assumed it for G star. So what we are saying is we are assuming Berge's conjecture for every graph here. So what we proved is this: every two connected cubic graph has perfect matching in its at most 5, if and only if every two connected cubic graph H admits Fulkerson power. So there are two for all instances, like the quantifiers here. For all G, phi of G less than equal to 5, if and only for all H Fulkerson curve, there is a Fulkerson curve for H. So this just says either both statements are true or both have counterexamples. And if you have a counterexample for Berge, we have a counterexample for Fulkerson, that is clear. But
The same graph.
Yeah, the same graph is a counterexample for Berge.
Fulkerson.
Fulkerson, yeah. Because you throw away one perfect matching and get it. So we know that the set of counterexamples, if they exist, they intersect, but we don't know if they are exactly the same. So this is still open. This problem is still open. Is this true? Fix a cubic graph first, and then ask if they are equivalent. So there is only one for all of them. So this is still open. And we'll just quickly look at one more result on this conjecture itself. We'll call it the Berge-Fulkerson Conjecture, or BF conjecture for short. And we'll be using this for Fulkerson to cover. But I'm not going to get into details. I'm only going to state it so it doesn't matter. From this, we can show same kind of arguments. G is a counterexample to the Berge-Fulkerson conjecture if and only if at least one of G1 and G2 is the counterexample. So there are no two cuts, which means the graph is 3 connected. 3 edge connected is the same as 3 vertex connected in full cubic. But 3 is sort of the maximum. Can we increase it? Is the question. And yeah, there are generalized notions of connectivity. So recall the concept of cuts. From this, we can get two new graphs. What we do is we look at this entire set X bar, shrink it into a little vertex, single vertex. That is one graph. And we look at X and shrink it into a single vertex. That is another graph. So this is the notation. I mean, it's not very relevant for the talk. And we call these little vertices the contraction vertices. And we also say that G is obtained by splicing G1 and G2. It's just two waveforms. Now, the point is, if you have a non-trivial 3 cut and you take the contractions, they are also cubic. And you can also show by similar counting, I mean, it's quite easy to show that if G is a counterexample, then at least, if and only if at least one of G1 and G2 is a counterexample. So the smallest counterexample does not contain any non-trivial type cuts.
3 cuts.
3 cuts. Yeah, the only 3 cuts are incident at a vertex. One sure is a single vertex. So we call those graphs essentially 4 edge connected. 3 connected cubic graphs that are free of non-trivial 3 cuts. And so we just discussed this. It's quite easy to prove. And there is one more notion of connectivity, cyclically connected. And it is exactly the same as essentially 4 edge connected for k equal to 4. And the result I read is by Mazzuoccolo and Mazzuoccolo. They proved that a smallest counterexample of the Berge-Fulkerson conjecture, if it exists, must be cyclically 5 edge connected. And
There's cyclically some condition on the cut.
yeah, so you just demand both the shores to contain a cycle. Then the size of the cut is large. But otherwise, you can allow small cuts. So this is particularly interesting.
Can be obtained by slicing.
Yeah, that is possible.
Yes. So the splicing operation is not
It's
unique.
not unique.
Maybe that is an important point here.
If your graph is really symmetric, it might be unique, but in general, it is.
Yes.
So this is interesting, particularly in this. Recall this for class one, the Berge-Fulkerson conjecture and many others can be easily verified. The only problematic ones are these. And there is a conjecture from 1980 by Eder and Swart, which says the cyclic edge connectivity of a snap is at most 6. So suppose we prove this conjecture and we get it to 6 and then to 7, then we have proved the Berge-Fulkerson conjecture.
But there's a six.
Yeah, same. So this is quite significant progress. Now this concludes the first part. In the second part, will be talking about lambda matchability.
Should we take a 2-minute break or should we just keep going or have a round of questions? Maybe we can just see if audience has any questions
Okay.
on the previous part and then move on. Because this is going to be
So this
Big
was
change of
part a
gears.
Sort of literature survey. The takeaway, the final results was proving the Berge-Fulkerson.
And we also have another paper on improving it to 6, but there are just a few cases of them.
This is the latest US result that you presented.
Oh yeah, there is another one that is related to this, but our results imply theirs, so I don't get into it.
oh yeah, but in this line of
Yeah, in this kind of
With the 5 years.
yeah, so they almost proved it for 6. The paper came out in March or May or something this year.
okay.
There's another paper which are not read.
So what do they prove in that? The cyclically 6 edge connected.
No,
No.
there are many cases, and for most cases they prove it.
Okay. But it's not
Yeah.
the 5 has not been made 6 so far. Okay.
It's very active or
Yeah.
it looks like a hard, like people are beta kind of. Yeah.
Yeah. So it is maybe you can mention that.
Oh yeah, we got to meet both the authors at University of Paderborn last November.
This November. Yeah.
Yeah, they were working on it. There are so many people working on just specifically on snacks.
There was a meeting on Snow.
Yes.
Yeah.
Yes. The whole meeting was on snark. We were the only non-snarky people there.
Any questions you have to investigate? Is it easy to see some simple constant bound on the perfect matching?
Perfect matching is off.
We like the matching color.
The easiest one is at least 3.
No, I think you are asking about upper bound. No.
Upper bound.
No, upper bound is known, right?
No.
Any upper bound is known?
No, as far as
And we're trying to show them something.
Yes.
But if I ask for 7 or something, it's very easy way of visualizing that.
oh, you mean
7 perfect
for
matches.
perfect matching cover? Oh, that exists, I think. I thought you were asking about the number of perfect matchings itself.
No, perfect matching cover.
So I think there is some result, right?
Okay.
Yeah, I don't recall exactly, but yeah, there is some result. Maybe I'll check and let you know. And one remark I forgot to make is this cyclic edge connectivity in general can be arbitrarily large.
Because it depends upon the removal of perfect matching. Somehow, there is not in the visualize how many odds cycles there are.
Oh yeah,
If I can somehow get a bound on the number of odds cycles, then it will
yeah. There is a whole lot of research done in this area. Like the least number of odd cycles in a 2-factor is also has a definition. It has a term. They call it oddness or something. they have many such parameters. They have a parameter called I forgot the term, but they have parameter for the number of edges that are not covered by three perfect matches. Minimum number of edges. There are so many parameters and like there's so much literature on just math, which I learned about only last year. Okay. So
Other questions?
there are
Big change of gears.
But it makes be an interesting question to ask for some constant bound or some small function bound.
Yeah, I think there exists a small constant bound. Could be even single digit, but I don't recall right.
Probably not easy to see it. I'm not even structure this not because it depends so much on the other concept.
I think getting a constant bound cannot be easy, but yeah.
But I mean, at least computationally, when we check, it can be done with the low sort of single digit number for up to order 30s or even 40. You know. But there should be results.
No, what do you mean computationally? I didn't get it.
Like the number of odds I
No, I think he's talking about the number of perfect matchings required to cover. Right?
cover. Yeah,
But that we are already. I mean, the conjecture is it is at most 5,
Yeah.
right?
the conjectures. Are,
And I think the conjecture has been verified.
Like, as n varies.
Okay. Oh yeah, it should have been verified by someone else, of course.
Yeah, yeah.
It
I
should
think
have been.
Goldgeber,
Otherwise, would have
yeah,
been
Jan Goldgeber and others have
Yeah.
verified these conjectures up to large number. But yeah,
Oh, yeah.
the constant bound, I don't think either of us remembers what it is, if there is one.
So you don't even know there's a constant bound. But a non-constant bound may be here.
Ah, that is quite easy. Linear is easy. Yeah, linear is quite easy. Like even yeah, for each edge
For
you can
each
just
edge, you simply take for perfect match.
Yeah.
You need something.
start linear is more interesting.
Long.
Could be true.
I mean, better be true.
If Berge is
If
True.
we don't know if the conjecture is true, yes.
Yeah.
Okay.
Maybe it might also be named as the curve of the graphs.
Mm.
To put in more parameters.
we get into the second part.
Okay.
This is also about a spanning subgraph of in which each vertex has 1 degree. So we call V matching a subgraph spanning subgraph M such that V has degree 3 and everyone else has degree 1. Here is one example. And since this looks like a lambda, we just call those vertices lambda matching vertices.
V is a vertex.
Yeah. So in these pink edges, V has degree 3, everyone else has degree 1.
It's just a slight variant of perfect.
And yeah, we just denote by lambda, uppercase lambda, the set of those vertices, and smaller case is the number of such vertices. I will just look. Yeah.
Lambda is set of lambda match.
And
This is the number of lambda match.
now we'll just quickly look at perfect matchings and come back to lambda matching.
So this is the combinatorial structure.
Yes.
Select the set of edges.
Yes.
Component has 4 vertices and
All edges. Yeah.
You have to look at cubic graph.
Oh yeah, this is all on cubic graphs. This entire thing is on cubic graphs.
And also not. You will soon go to matching curve graphs.
Okay.
Okay.
I mean, we apply the theory of matching curve graphs
Okay.
two cubic graphs again. So we have this, and this part is about proving a lower bound on lambda. We'll look at perfect matchings again and come back. A graph is matchable if it has a perfect matching, just a name. And let's say you have a set of vertices which, when you delete, you get these many components of odd order and some components of even order. But the number of vertices is you deleted is less than the number of odd components. Then it is clear by if there is a perfect matching by the parity lemma, there is at least one edge coming out of it and one edge coming out of each odd component because it is odd. And there are only 4 vertices with 6 odd components. So there cannot be a perfect matching. That's something easy to see. And we'll call such a set a touch set. And it's easy to observe that if G has a touch set, then G is not matchable. And touch showed it is if and only. And if you have a graph that is matchable, this number can at most be equal to the cardinality of T. So we'll call such a set a barrier. If you delete 4 vertices and have exactly 4 odd components, then we'll call it a barrier. And number of even components can be anything, 0 or arbitrarily large, doesn't matter. So let G be a matchable graph. It has a perfect matching. So it is easy to show G minus U minus B is not matchable if and only if there is a barrier containing both U and V. Because G minus U minus V has a touch set, that will be just these 3 vertices. When you put U and V back, you have to destroy the touch set because G was matchable. So this is the structure. And if G minus U minus V is matchable for every distinct pair UV, we call it a bicritical graph, similar to factor critical. Now, a graph is bicritical if and only if something about the barriers. So G minus U minus V is matchable for every pair. If and only if, yeah.
There is a barrier for every pair of vertices. There is a barrier.
No, I'm saying this is matchable. Here there is a not matchable.
You just have to put a not somewhere, then the statement is correct.
Yeah.
For every pair of vertices, there is not a barrier containing both of them. You said there is a barrier. You just put not, then it's correct.
Yeah. So in other words, every barrier is either the entry set or a singleton. And we call such barriers a trivial barrier. We'll just find this useful later. And for a technicality, we put this condition has at least 4 vertices. We'll see why. Just to exclude this graph, but why do we want to exclude it? It will be clear soon. Next, we go back to lambda matchability. Let's take G, and it has 3 distinct neighbors, V1, V2, V3. We can say V is lambda matchable if and only if some graph has a perfect matching.
G minus V1
And also,
yeah.
Right.
yeah.
Also.
So we get this. So in particular, let's say G is bipartite. Can we say anything about lambda matchability using this? We have 2 color classes, black and white. You delete 1 black vertex, 3 white vertices. So the remaining graph cannot have a perfect match. So we have one set of vertices, black vertices and white vertices. And in G minus V minus neighborhood of V, you delete 1 black vertex, 3 white vertices.
And the original graph is cubic, so
Oh, yeah.
black and white are
It's all cubic.
equicardinal.
So black and white have equicardinal. So now no vertex is lambda. Is that clear? Yeah, we only care about 2 connected cubic graphs. So each side has equal number of vertices. If you delete one black and three white, there is no way you can match it. Then it is 0. And what about bicritical graphs? We call u minus b is matchable for each distinct pair. This is not as straightforward as this, but still quite easy. So just think of what two vertices to delete here. Okay, so let's say I delete V2 and V3. I take a perfect matching. So now every vertex has degree 1 and V2 and V3 have degree 0. Now I'll just add VV2 and VV3 to this set of edges. Now V has degree 3 and everyone has degree 1. So every vertex is lambda matchable. Just one technical condition. We are assuming the vertex V has 3 distinct neighbors. So if this is your graph, it fails. That is why we added that technical condition in the definition of bicritical.
Number of vertices.
Yeah,
Oh, that is
order.
good. Capital N. Sorry. NG is number of vertices.
Number.
Yeah, order.
So for each vertex, you're going to get.
Yeah. So we saw lambda 0 for bypass.
Argument for the previous one. So if it is bicritical, look at the vertex.
Yeah.
Let's say its neighbors are V1, V2, V3.
Yes.
V1, V2, V3 to graph. And only where we want the V could have been matched is the right of the print.
Yeah.
To the rest of them.
Yes. Yeah. Maybe I should repeat cubic every now and then. So we saw lambda is 0 for bipartite ones. Chen, Lu, and Zhang, they show it is at least 4 for non-bipartite 2 connected ones. And if it is 3 connected, it is at least 6 for a large enough graph. And they also show there is no linear form, linear lower bound. Yeah, they construct 3 connected non-bipartite cubic graphs of arbitrarily large order with lambda exactly equal to 6. So hopes are not all hopes are lost though. We'll apply the theory of perfect matchings, and we will show lower bounds on lambda based on matching theoretic invariance that derives from the work of Loas. We'll see it soon. And we also solve one of their open problems. I'll show you. Next, we'll look at the matching curve graph theory. Cut is tight if for any perfect matching, the intersection with the cut is 1.
So you're going to prove a goal.
Yeah.
Not the value of
Yes.
the two connected.
Cubic graphs.
You know the vacuum also proves that.
Yeah.
For infinitely easy.
No, that is something they prove in their own paper. Oh, okay. By their result, I mean these lower bounds. Our lower bounds imply their lower bounds. Yeah.
Yeah, but the proposition is actually
Yeah.
But those,
yes.
But this is quite an easy.
This is actually very easy. The proposition is very straightforward.
It could be an illustration. So, yeah, we call a cut a tight cut if the intersection with the cut of any perfect matching with the cut is exactly 1. One easy example is every trivial cut is a tight cut if you have only single vertex on one side. Here is one example. The reason it is interesting is we can now take the partial x contractions, and if the cut is non-trivial, we get 2 strictly smaller graphs. Plus, these edges appear here too, sort of. We can use the same labels to denote these edges. And if you fix any perfect matching of the graph on the left side, the contraction vertex x bar has to be matched by some edge. And you can also pick any perfect matching that contains this same edge on the right side. Now we have two perfect matchings. If you take the union, it will be a perfect matching in the big graph. And we find this useful for proving many things.
Yes, I think you didn't emphasize on the fact that the two smaller graphs are matching covered.
Oh yeah.
I mean, you implicitly meant that, but yeah.
Yes, I did. Sorry. Yeah, it is quite easy to show both are matching covered, like other contractions. Yeah. Now you can define what is called the type cut decomposition procedure. You can take any matching covered graph. There's going to be either there's no non-trivial type cut or there is. If there is many, you just pick any one arbitrarily and consider the contractions. And if you reach a point where there is no non-trivial type cuts, we just stop there. Otherwise, we keep going. And at the end, we'll get a list of graphs which are free of non-trivial type cuts. There's more names again, so in terms of the bipartite ones are called braces, and the non-bipartite ones are called bricks. Now the question that arises is, if I start with some graph and if someone else starts with the same graph and applies this procedure, since I'm making an arbitrary choice, will we end up with the same list of bricks and braces? The answer is true up to the multiplicities of edges, which means when we do this process, and if both of us take the underlying simple graphs, then we get exactly the same graphs. Otherwise, the multiplicity of edges would be different. So that is what lowest row. No, it's not trivial, but due to a result by Edmonds-Lowers and Fulkerson, it is global and at most n square n cube maybe.
Yeah, it's polyton.
So then we can define these invariants, number of bricks of G, and even this is also an invariant. The sums of all the orders of the bricks of G. And we'll just show lambda is at least beta. And the lambda at least 4 is their result. And it comes from the fact that K4 is the smallest brick.
Right. So if you have a non-bipartite graph, then you will have at least one brick, and then you get at least 4. It follows immediately.
Yeah, so intuitively, one would think if you start with the bipartite graphs, you will never get bricks. That is true. And also, you would think if you start with the non-bipartite one, you will get at least one brick. That is also true. Yeah, so we'll prove this. Just give you some intuition first. Recall that in bicritical graphs, every vertex is lambda matchable. And Edmonds-Lowers and Fulkerson, they proved a characterization of bricks, which implies that for cubic case, it is exactly the same as bicritical. So here for bricks, we already know this result, lambda is at least beta. So one would expect each brick contributes order many lambda matchable vertices. It's just very loose. It's nothing very precise. And consequently, G has at least beta mean. That turns out to be true. Recall graph of order at least 4 is bicritical if only each of its variants is trivial. So if there is no non-trivial barrier, we'll come. Otherwise, we'll use the non-trivial barrier as the induction rule.
Maybe you can wait to make sure whether people got the fact that for bricks it is true. For bricks, beta is equal to
n.
N.
And lambda
is equal to N. Right. Fix the statements.
So
Yeah, I think you can continue.
so let's take any non-trivial barrier. Now the number of odd components is exactly the same as the number of vertices we deleted. And if we start with the matching code graph, it's easy to show there is no even component. And if you and this gives us these natural effects, and these are all considered the show one show to be, I mean both the shows to be odd. There are odd number of vertices, and by the parity lemma for any perfect matching, the intersection here is odd. Here is also odd everywhere. And if you look at it from the top, there is exactly one edge coming out here, one edge coming out from the other vertex, and so on. So everywhere it is going to be exactly one. So these are all tight curves. What I'll do is take a couple of steps. I mean, not couple, a lot of steps. Yes.
In a matching code graph.
Yeah, in a matching code graph.
That's it.
Yeah. So these steps should be tight now by counting. Now I'll take a few steps of the tight decomposition procedure at once. Those that have an so I have this. I'll shrink every vertex into a single vertex.
Every component.
Every component J1, J2, J3 into a single vertex. Now I have a bipartite matching code graph. Bipartite graph and matching code because shrinking a type that shore gives you the matching code. And I can also do the same with the other shore for each of them. And now there's a correspondence between this type at C1, this vertex A1, this graph G1. Right? Okay. Maybe you can. Yeah.
Even the trivial ones.
Yes.
Even the trivial ones. It won't do anything.
Yeah.
Yeah.
So. Yeah, and I can also do the same thing for each of these. I can contact the other show. Yeah.
For each odd component, shrink the complement.
So you can think of it as I'm shrinking C1 first. I'll get G1 and some other graph where this is a single vertex and these still remain. And then I can do it one by one. I'll get at the end I'll get this. And any application of tight decomposition procedure to G that will give the bits and braces of union of bits and braces of these graphs. And recall I told you bipartite ones don't give you bricks, right? So we have this beta of G is exactly equal to the summation of beta of Gx. Because each brick comes from the non-bipartite ones. I mean, there could be some bipartite ones here also. Then beta will be 0 plus.
Like your G3.
Yeah.
Right? Your G3 is just theta, that will give you beta 0.
And in the procedure, we don't consider trivial factors, but considering it won't give harm us in this case for beta. Now, let's see what happens if the graph is cubic. I'll just add 3 edges here for every vertex. And we know it is a 2-connected cubic graph. So each cut has at least 2 edges coming out. And by the parity lemma, the number is odd. So it has to be at least 3 everywhere. Now it is here, it is exactly 3 everywhere. So the point is the core and the D fragments are all also free. I don't think I said the word D fragments yet. We call these D fragments. These are fragments of G coming from the barrier. So we have this. we'll apply this concept and prove lambda is at least beta. Now, if you have a non-trivial barrier, there are two types of vertices. One inside the barrier and one outside the barrier. And for each of those, we have characterizations when they are lambda matchable. A vertex inside, outside a barrier is lambda matchable, and only if it is lambda matchable in the corresponding V fragment. And the next statement is quite complex. It is the maybe I mean should I skip the?
I think you can complete the proof of the three connected case and then go fast and finish it off.
Oh, there is only one slide after.
Yeah, okay.
So
Shall we take another 10 minutes or is that okay? Okay. You sure?
Yeah.
Okay, sure. What about the others? Is it okay to take another 10 minutes or so? Well, anyways, we're recording it, so we'll just share the link. Okay. Are you okay with that? Okay. Okay.
okay. Now let's say there's a V matching in this graph that will denoted by R angle this. Now by a parity lemma, again the intersection with each of these is odd. So the only option is to be one of them to be 3 and everyone else to be 1 for example. Let's say it happens at C2. Now I look at the core and this corresponding fragment, B fragment. Here, if I look at the restriction of those edges to these graphs, I have this contraction vertex of G2 to be a lambda matchable vertex. There's a V2 matching here. And here we have a strange thing going on. We saw lambda 0 for bipartite ones, but we can allow 2 of them to have degree 3. This is possible, and we just call them. We'll call such a matching an AB matching. Degree of A and B is 3, and degree of every other vertex is 1. So what we have essentially proved is, if B is lambda matchable in G, then there exists some A in the core such that B and A together form a lambda matchable pair, and in the corresponding B fragment, the one that corresponds to A2, that is G2, the contraction vertex B2 is lambda matchable. This correspondence is going on, and the reverse direction is also quite easy. You just start with this. You first look at the graph that is obtained by splicing H with G2 at just this vertex. I have this going on. Here there is a V match. And now, if you recall, with right cuts, I can fix perfect matching of the V fragment and just take the union to get the perfect matching. I'll do the same thing here and blow up each of these single vertices to get the V matching in the big graph. So this is if and only if. And we need one more lemma, which I'll not do. I'll just state it. For every connected cubic bipartite graph, if there is an edge AB, then the pair AB is lambda matchable. This is something quite easy to do. Here is an example. This is the graph obtained when you slice 2 K3Ps. And in this case, the graph is unique. So here is an edge and the pair AB is lambda matchable. A and B have degree 3, everyone else has degree. Next, we'll look at the main theorem proof for there's 2 next. Ignore it. Yeah, then proof idea for 2 connected. It's just the same thing we already discussed in the first part. So we'll prove this. And I also state the characterization of equality, but we'll not prove it in this one. If G is bipartite, then both are 0. There is no lambda matchable vertex, we already saw. And there is no bricks, I just told you. It's believable, I guess. Otherwise, lambda equal to B, beta holds, if and only if beta equal to M holds. That is, this value, change value beta, it's exactly equal to the order. if and only if it belongs to some family. I will show you the family quickly. And if you look at this, you might have a question: why is lambda equal to n not here? Lambda equal to beta is here, beta equal to n is here. Turns out lambda equal to n is just another way of saying every vertex is lambda matchable. Turns out there are more graphs for which that is.
That is the order of things.
Yeah, but disjoint, no, it's a connected graph. I mean,
Maybe different things.
yeah. But in those cases, lambda will be strictly greater than beta. I can show you examples if you want later. Okay. Here is one example. This is the graph you get when you slice K4 with K33. When it is K4 and K33, again it's unique. The green vertices are lambda matchable and the red ones are not. It's quite easy to check. Here the beta value is 4 because K4 is the only brick. The order is 8 and lambda is 6. So lambda is placed as beta. This recursive definition of script G is quite easy. You first put all the cubic bricks in script G. Now you take any three-connected 5.8 cubic graph. We are just artificially creating a barrier now. You take any script B, cardinal TTB members of script G. Now you splice however you want. Here, respecting the correspondence, and this graph is also in script G. Now in the resultant graph, B will be a barrier. And this is one example that is the simplest one is taking H to be K33 and everyone else is K4. This is the simplest example. That is not a brick.
So for this graph, lambda equal to beta
Equal to
n.
Yeah.
Equal to 12.
Yeah, everything is. And we'll only prove this one, the inequality, and we'll use induction as we saw earlier for bicritical equivalently bricks. This holds. Lambda is beta is equal to n by definition, and every vertex is lambda matchable. Otherwise, he has a non-trivial barrier. Now we'll apply all the three lemmas that we saw. This is the situation we have, and we just want to count the number of lambda matchable vertices of G. Recall that by the outside barrier lemma, every vertex that is lambda matchable here is also lambda matchable in the big graph. So we have this lambda of G is actually summation of lambda of G, but is there anything wrong with it? I mean, the contraction vertices don't exist here. So I have to account for that. Let's say V1 and V2 are lambda matchable, V3 and V4 are not. If I take this sum, I'll get 2 extra variants. So I'll just define the corresponding subset of A. If V1 and V2 are lambda matchable, I'll define A prime to be A1 and A2. And that set is here. If I subtract that, it is fine. But this only counts the vertices outside the barrier. I also want to count the ones inside the barrier that are lambda matchable. I just define this subset, the lambda matchable vertices, and just add it. Nothing fancy. Now we use the outside barrier lemma. Inside barrier lemma. It says a vertex, so let's say V1 is lambda matchable here, if and only if there is some other vertex here such that it is a lambda matchable pair with V1, and in the corresponding V fragment, the contraction vertex is lambda matchable. In other words, since we defined A prime already, we just want the lambda matchable partner, if I may call it so, in A prime. So I'll just define it to be that every vertex here, I'll collect all the vertices here such that it has a lambda matchable partner in A prime. But still I can't do anything to this. I need more information. That is where I'll use the adjacency lemma. It says if there is an edge in the bipartite graph, three connected bipartite cubic graph, edge AB, then AB is a lambda matchable pair, which means the entire neighborhood of A prime is contained in B prime. Now I'll just replace this with the neighborhood and put greater than equal instead of equal. And I just rearrange this. Does this remind you of anything? Sorry. Yeah. False here. So these are matching to our graphs. So this is clearly at least we have this. Now I finally use the induction hypothesis and show this lambda is at least beta for each gi. Now I have this. Now I'll use this fact. Beta, all the beta comes from gi's. So summation beta of gi is just beta of gi. And now I have this whole chain where lambda is at least beta. And we just showed this first part. And for two connected also, if you use this idea, you can show that the set of lambda matchable vertices of G is just the disjoint union of flows in G1 and G. So you can show this just directly like this. And script G prime, there is a definition. So we can define two-cut decomposition similar to the type-cut decomposition. If you find a two-cut, take G1 and G2, keep going. And it turns out even there the set of graphs you get are unique. It was proved as early as 1980s. And this script.
You won't get multiple edges this time. All right, you could get multiple edges. Yeah, you keep them. Now you don't need to take simple also. Now the exact sets will be same.
Yeah.
Yeah.
And yeah, script G prime is just defined to be all these three connected graphs. Yeah, in general also there is a result.
For R graphs. Yeah.
No, not just R.
Sure.
Edmonds and Cunningham, their proof works for any
two connected graphs, you can break it into three connected pieces. And you can so there they deal with two vertex cuts. But essentially if you apply the same thing to cubic graphs, two vertex cuts and two edge cuts are not that different. So you can get this from there as a corollary.
the degree is they find that no vertex. Yeah. For in general, they provide for four vertex.
Yeah.
And in fact, they don't directly prove this. It's a parallel. Yeah, and you have to define two-cut decomposition appropriately.
Yeah.
So this G prime is nothing but all the three connected pieces of the graph you get should be either in G or it should be bipartite. Because bipartite it has nothing. And even for the number of graphs we go along that looks change like this. Here B prime is just the number of braces, but we add one more condition, order at least 6. Sorry. This is the number of lambda matchable pairs in the bipartite. So here you only get braces and we found only those of order at least 6. And beta prime is sort of like beta in this case. There we count only the number of vertices and it was the order. Here it turns out that in braces every pair is lambda matchable. So it's 10 by 2 here on one side and 10 by 2 on the other side. So the number of pairs is n by 2 the whole square. We just take that sum over each place. And here's one example. For K3 it is 3 times 3 is 9. Since there are 2, we add those beta primes to sorry, 18 for this and B prime is
B prime is 2.
because there are 2 braces. K3 is a braces. The gap, I mean, so for any cubic graph, you can construct such a thing. Either you have a brick, or there is a non-barrier and this whole thing is going on. So any cubic graph can be viewed as a, I mean, I defined a family of cubic graphs. Yeah. Here, instead of splicing it everywhere, if you allow non-splicing, you can generate all cubic graphs. And at one step of splicing, you can actually see something about the number of lambda matchable vertices of this versus there you can. Yeah, if you don't end up splicing somewhere, you should yeah, one could do that. I mean, so we characterize those for which every vertex is lambda matchable. There we do a strange thing. I mean, I wouldn't be happy to explain, but it might be. Yeah. But if you look at that idea can be extended, if I'm not wrong, for any constant gap between lambda and beta, you can generate all those. Gap in general can be unbound. So beta for any k, I can give you a graph with lambda equal to k, but beta is just 4.
Any other questions? Okay, if not, let's thank Santhosh again. Okay.
If there are any comments on how I presented things, please let me know. Okay.
I think you should not stop recording. Oh, it's on the right side.
Oh, here, okay.